Today in DC electrical circuits, we're taking a look at lab number 3, resistor color code. The objective of this exercise is to become familiar with the measurement of resistance values using a digital multimeter, often abbreviated as DMM. A second objective is to learn the resistor color code. Now, under reference sections, I'm referring to Sham's Outline, Basic Electricity, 2nd edition, and now we've moved on to Chapter 3, Resistance and Fixed Resistors. So Chapter 3 covers a lot of topics, and it's titled Ohm's Law and Power. It has a whole section on resistance, and you'll notice Figure 3-4 is using the schematic symbol for a resistor, so keep in mind that we do need to be able to convert symbols to their physical components. In this lab, we're going to be working with fixed resistors only. In a future lab, we'll be dealing with variable resistors called potentiometers or rheostats, depending on how they're wired into the circuit. Now, we order our parts kits from Abra Electronics, and in every kit you get one of these business cards. And if you turn it over, it gives you resistor color code charts for the resistors. So we're going to go over how to read the colors on a standard 4-band resistor. Now, I've given you a fairly large theory overview that you should read through. The resistor is perhaps the most fundamental of all electrical devices. Its fundamental attribute is the restriction of electrical current flow. So the greater the resistance, the greater the restriction of current. Now, resistance is measured in ohms, and the measurement of resistance in unpowered circuits may be performed with a digital multimeter. Now, keep in mind the statement says the measurement of resistance in unpowered circuits. So it's very important that you take a resistor out of a circuit before you can measure its resistance. You can't measure the resistance of a resistor in circuit because you're measuring the entire resistance of the circuit, and it will be significantly lower than what the resistor value should be. Also, if it's a powered circuit, the power will flow back into the meter, giving a totally inaccurate reading, if not destroying your meter. They talk about the resistor color code typically uses 4 color bands, and those are going to be the ones that are in our kit. The first 2 bands indicate the precision value, okay, while the 3rd band indicates the power of 10 applied, or the number of zeros added, and the 4th band indicates the tolerance. Now, when looking at resistors, it's important to note the physical size of the resistor really depends on the wattage of the resistor. So a higher wattage resistor is going to be much larger than a smaller wattage resistor. Now, most of our components that we get in are going to be of the 1/4 watt size. And if you're using this chart to measure the wattage size of your resistors, notice this chart is shown at 2 times the normal size. Each color in the code represents a numerical number. So you can see black represents 0, brown equals 1, red equals 2, orange equals 3. Try to memorize those 4 numbers and their colors. 4 equals yellow, 5 is green, 6 is blue, 7 is violet, 8 is gray, and 9 is white. So the typical resistor that we have in our parts kit are of the 4 color band type. You'll notice one color band is kind of separated from the other 3. On this example, we have a brown band, a red band, an orange band, and a silver band. So looking these up, we can see that brown represents 1, and red in the second band represents 2, and orange in the third band represents a multiplier of 1000. So in this case, we can see it's 1, 2, followed by 3 zeros, or 12,000 ohms. Typically written as 12K ohms. The last band, the silver band, is the tolerance band. And typically we get gold banded resistors in here, so they're typically 5% tolerance. In the example here, they've put a silver band on this resistor, and the silver band is a 10% tolerance. So in this example of 12K ohms, we can see that it can equal anywhere from 12K minus 10%, which is 1,200. So the resistor value could be 10,800 ohms, or it could be the 12,000 plus the 10%, which is plus 1,200. So that would be the 13,200. So a 12K resistor with a silver tolerance band could be anywhere between 10,800 ohms and 13,200 ohms. They give you a second example of a 470K ohm resistor with a 5% tolerance on it. So you can see the color bands were yellow, violet, yellow. So yellow is 4, violet is 7, yellow is 4. So that would be 47 with 4 zeros after it. So in proper engineering notation, that would be 470K, K being 3 zeros. Then they give you an example of a mnemonic. It's a memory aid to help you remember all the colors. So they're giving you black bears rob our yummy goodies, beating various gray wolves. There are a lot of other mnemonics out there to help you remember the resistor color codes. It's up to you to pick one that you like. Now we're going to be measuring resistance with a DMM. It's a fairly easy process. The only thing to remember is that our meters are auto-ranging. So wherever you see in the lab here to change the range to the appropriate range, our meter will auto-range for you. The other thing you need to keep in mind is that we're going to be using banana leads with those alligator clips on, because if we touch the resistor with our hands, we're going to change the resistance that the meter reads. I also give you the formula for calculating percent error, so keep this handy with you. You'll be using it in the rest of your labs this semester. So under the equipment that we're going to be using today, we have a digital multimeter sitting on the student bench. It's the Mastech MSM 9803, and we're not going to bother trying to find the serial number. It's somewhere underneath the equipment, and we have it strapped together. As with all my labs, when I introduce you to a new component we haven't used before, such as these resistors, I try and find an appropriate graphic on the internet. Be careful, they're not always correct on the internet, and it took me a while to find the correct ones. So when you're looking at something like a 68 ohm resistor, the color bands on it should be blue, gray, black. And the majority of our resistance have a gold tolerance band, which is 5%. So these labs are actually in color, so if you look in the description under the video, you'll be able to see a PDF. If you click on it, it'll bring up the lab in color, and you can see your resistor color bands. So under procedure, step number 1 it says given the nominal values and tolerances in table 3.1, determine and record the corresponding color code bands. So we're not physically looking for the resistors, we're just using the numbers given as an example to fill in our table. The first example is 27 ohms at 10% tolerance. So the first digit is 2, and the number 2 is red, so the first band is red. The second digit is 7. So looking up 7 on the color table, you can see it's violet. So write violet in for band 2. Band 3 is the multiplier. In this case, we're going to multiply the number by 1. So 10 to the power of 0 is 1, or you can think of it as 0 zeros. So this is a 27 ohm resistor. The first band is 2, or red. The second band is 7, or violet. The third band is the multiplier, and there's 0 zeros after the number. So that would be black. Then the tolerance is 10%, and 10% is silver. You may complete the table on your own. Under procedure, step number 2, it says given the color codes in table 3.2, determine and record the nominal value, tolerance, and the minimum maximum acceptable values. And once again, we're not looking for these resistors in our parts kit. So on the first line of table 3.2, you can see we've got a resistor that's red, red, black, silver. They want to know what the nominal, or what the value of red, red, black is, and the tolerance for silver. So red is 2, red is 2, and black is 0. So notice there's 0 zeros, so that means that the answer is 22 ohms. The tolerance is silver. Silver is plus or minus 10%. Now they want to know what the minimum and maximum value of this resistor is going to be for it to be within tolerance. To find the percentage, you take 22, multiply it by 0.1, and that will be equal to 2.2 ohms. So a silver tolerance of plus or minus 10% is plus or minus 2.2 ohms. So to find the minimum value, you take 22 minus the 2.2 ohms, or minus 10%, and that works out to 19.8 ohms. To find the maximum, you take the 22 ohms and you add the 2.2 ohms to get the value of 24.2 ohms. You can complete the rest of table 3.2 on your own. Under procedure, step number 3, we're going to obtain a resistor equal to the first value, 10 ohms, listed in table 3.3 from your parts kit. So now we actually have to look through our parts kit for the correct resistor, and I just showed you on a previous page that I do tell you what those colors will be. It says the resistor will have a tolerance band, so we're to record its value in the first column of table 3.3 under value, and most of our resistors come in plus or minus 5% quarter watt sizes, so these are probably going to be gold bands. We're to determine the minimum and maximum acceptable values based on the nominal value and tolerance. The nominal value is the expected value, so if we are using a 10 ohm resistor, the nominal value should be 10 ohms. So we're to record these values in table 3.3, and then using the DMM, measure the actual value of the resistor and record it in table 3.3. So this is table 3.3, and the first value that we're supposed to check is the 10 ohm resistor, and we don't know what the tolerance is right now, so we're going to check that resistor by taking it out of our parts kit. Now you'll notice on the front page I've given you the resistors that we're going to be using in this lab. I won't be doing it every week, but when I introduce a new part I like to get you a picture of it so you can see what it looks like. And the first resistor that we're going to be using is the 10 ohm resistor, and its color codes are 1, which is brown, 0, which is black, and there's 0 zeros after it, so that's 10 to the power of 0. So that band will be black, and it's probably going to be plus or minus 5%, so it should probably be gold. So what I like to do before I start a lab is to get all my parts out. So these are all the resistors that are in table 3.3. So you can see at this end I have the 10 ohm resistor, which is the brown, black, black, and followed by the 68 ohm, the 150 ohm, all the way down to the 5.6 meg ohm resistor. It's really handy if you get them out maybe the night before you come to a lab, and I just put mine in a spare piece of foam so that they're ready to go the next day. So looking at my first resistor, you can see it's brown, black, black, and the last band is gold. So that's plus or minus 5%. So the first thing that I record in my table is that it's going to be 5%. So to calculate the minimum and maximum, the first thing I like to do is take my 10 ohms and multiply it by 5%. To enter that on your calculator, you'll type in 10 times 0.05, and the answer is going to be equal to 0.5. So the minimum is equal to 10 minus 0.5, and that equals 9.5 ohms. The maximum is equal to 10 plus 0.5, so that's equal to 10.5 ohms. So the digital multimeter that we're going to be using is the Mastech MSM 9803. And to measure resistance, you move the dial round to the ohm symbol, and we're going to be using the red lead in the red hole with the little ohm symbol on it, and the black lead goes into the common terminal. And I want you to notice, with nothing hooked up to it, when it's reading infinite resistance, you'll notice that the meter is flashing 4000, and it's on the meg ohm range. So this indicates infinity. So to take a resistance reading, I have the black going to one alligator lead, and I have the red lead going to the other alligator lead, and into the alligators I have my 10 ohm resistor. A resistor does not have polarity, so it doesn't matter which way around you put it in. And you can see my reading on the meter is 9.8 ohms. You can manually change the range settings. And as you increase the ranges, you can see the number disappears off of the scale. So on the meg ohm range, it's reading 0 ohms. And when you put it on the ohm scale, it reads 9.8 ohms. And to put it back in auto ranging, just hold down the range button, and auto will be displayed in the top left hand corner. So in table 3.3, I'm going to record my reading of 9.8 ohms. So under procedure, step number 4, determine the deviation percentage of this component and record it in table 3.3. I've included the formula to calculate deviation, so we're going to use the percent error formula shown below. So percent error is equal to the absolute value, so those two bars mean absolute value, of the theoretical value, or the nominal value, or the known value, right, minus whatever your experimental value is. So that's the reading on the digital multimeter. And we divide that by the theoretical value, and we multiply it by 100 to give us a percent error. One last note, it says circle the deviation if the resistor is out of tolerance. So we need to keep our eye on it and make sure that what we calculate does not deviate from the minimum and maximum acceptable values. So on my 10 ohm resistor, it did have a 5% tolerance. So it has a minimum value of 9.5 ohms and a maximum value of 10.5 ohms. And I've measured it to be 9.8 ohms. So now I need to calculate the percent deviation. So in order to calculate the percent deviation, we take the theoretical value of 10 ohms, we subtract the experimental value of 9.8, and if you're doing it on your calculator, you might want to put brackets around it, so you do the 10 minus the 9.8 first, and then we divide it by the theoretical value, which is the 10 ohms. Then we take the absolute value of that, so if it comes out to negative, just take the positive part of the number and multiply it by 100. In my case, it worked out to 2%. Now, since 2% is less than 5%, I do not need to circle my deviation. So under procedure, step number 5, we're to repeat step 3 for the remaining resistors in table 3.3. So I'm going to leave the rest of table 3.3 for you to fill in and do the calculations yourself. So on the last page of the lab, we have 3 questions for you to answer and hand in based on your calculations and observations during the lab. Remember, when you've completed your lab, show it to your instructor during class so that they can initial it to indicate that it is complete.